Hello everyone and welcome. Alright, this video is going to be the completion of the notes we didn't quite get through in class today. So in class we finished talking about exact equations. We looked at our first example that was exact. So we were able to take our differential equation, which was right here. We checked each piece, determined it was exact, and we proceeded with the solution process. However, what if we have a differential equation like this? Right, where if we go to test, so if this is our f and this is our little g, if we calculate our f sub y, we would get the partial of the first piece with respect to y is going to be x. If we calculate our g sub x, that's the partial of the second piece with respect to x, we're going to get 2x minus 1 over y. These two guys are not equal, so this differential equation is not exact. So our goal here is to say, can we multiply by some special function, some special integrating factor to make this differential equation exact? That's our goal. Now there's two ways we can go through this process. We can either use the formula approach we talked about in class, or we can use the theoretical approach. Now the formula approach says, well, if we would calculate f sub y minus g sub x, I guess that value would have been x minus 2x plus 1 over y if I distribute that negative, which should simplify to negative x plus 1 over y. Okay, now if f sub y minus g sub x is 0, then our differential equation is exact. If it's not 0, then one thing we could do is divide through by g. In other words, divide through by x squared minus x over y plus 1, x squared minus x over y plus 1, and see, is this just a function of x? If it's just a function of x, then our integrating factor would be e raised to the integral of all of that junk. Now in this specific case, I'm looking at that expression, and it doesn't look like I'll be able to do anything with that to simplify to somehow eliminate those y pieces. So in this case, it doesn't seem to work. Now, if f sub y minus g sub x is not equal to 0, the other thing we could do is instead divide through by negative f. So now we have negative x plus 1 over y. That again is our f sub y minus g sub x, but now we're going to divide through by f, negative f, which is negative xy plus 1, because here is our f and it's negative f. Now, the idea here is if this is just a function of y, then we could create a integrating factor using a similar formula here, where we'd say e raised to the integral of all this stuff. Now at first glance, this doesn't look to be a function of just y. However, if we do a little algebra on this guy, in other words, if I were to maybe multiply top and bottom by y, so I'm multiplying my fraction by 1, so I'm not changing the value, but in a special form. If I do that, I get negative xy plus 1 in the numerator. I get negative xy plus 1, negative xy plus 1 all times y in the denominator. And what I see is then I can kind of cancel these two terms. So I'm left with really just 1 over y. So it turns out that f sub y minus g sub x minus f is just a function of y. So this is just a function of y, therefore u will be equal to e raised to the integral of all this stuff, and my f sub y minus g sub x divided by negative f. And if I integrate that with respect to y, this will be my integrating factor. So in our case, we have e to the integral of 1 over y dy. So this is e to the natural log of y. So in other words, this is y. So in this case, my integrating factor should be y. In other words, if I take my original differential equation, I multiply through by y, what would I get? I'd get xy squared minus y dx plus y times the second piece, so that would be x squared y minus x plus y dy equals 0. This differential should be exact. We can actually test that real quick here. If I take the partial of the first thing with respect to y, that would be 2xy minus 1. If I take the partial of the second thing with respect to x, so this is g sub x here, this new g, I would get 2xy minus 1. So yes, this new differential equation is exact. So now that I can tell it is exact, now I would go through my regular procedure for solving an exact differential equation. That means this first piece is supposed to be the partial of my mystery function with respect to x, and the second piece is supposed to be the partial of my mystery function with respect to y. And remember, in the end, my solution is my function equals c. So I can integrate, so if f sub x is equal to xy squared minus y, I can integrate this thing with respect to x to get my first expression for my missing function x. In this case, integrating with respect to x would give me x squared over 2 times y squared minus y times x plus some unknown function of y. Right, so this is kind of our generalized constant, sort of, in this case. Any function of y, if I take the partial with respect to x of it, will go to 0. Therefore, I'll get back to my original function here. Right, so I'm adding that psi of y. Now, similarly, if my second piece was f sub y equals x squared y minus x plus y, integrating here with respect to y should also give me an expression for f. In this case, I'd get x squared y squared over 2 minus xy plus y squared over 2 plus potentially some unknown function of x. Now I'm really comparing these two expressions, right? So my f function is going to be this guy, x squared y squared over 2 minus xy here, or yx, minus yx, the next piece, plus my unknown function of y. Now I look to my other piece, that's not a function of just y, that's not a function of just y. This right here is a function of just y. That must be my missing psi of y. So that's my unknown function f. This guy equal to constant is my solution. Okay, so this is an example of calculating the integrating factor needed to make this originally not exact equation into an exact equation, and then finishing the solution process. All right, the last piece we didn't talk about existence and uniqueness theorems, and we essentially had two theorems here, one for linear differential equations, one for the general first order. So this first differential equation we see is linear. There's my dy dx raised to the first power, and y raised to the first power. So this is just linear. So if it's linear, well, then I can put it in a standard form. In this case, I would have to divide through by my 2x, and I have to subtract over my 2y. So I subtract over 2y, divide through by 2x. Negative 4x cubed divided by 2x. So I'm putting my differential equation into the form dy dx plus some function of x times y equals some function of x. And our theorem states that we're basically checking p of x and f of x to see if there's any x values that break stuff, right? So in other words, there will exist a unique solution at y of x sub 0 equals y sub 0, right? As long as x sub 0 is in some interval where p of x and f of x is well defined. So if we go back to our example, we're going to simplify this a little bit. To write this as minus y over x equals minus 2x squared. And I'm checking for my problematic x values in this case. Here I can see, because of x in the denominator, that x can't be equal to 0. That means I have two potential solution intervals, from negative infinity to 0 or from 0 to infinity. So this would mean that for my stated initial condition, there would not exist a unique solution. Right? So there would not exist a unique solution. Now, if I had a different initial condition, for instance, for example, if I looked at y of 1 equals 4, right? Now, because my initial x value is 0, I know my solution starts in this interval. So I would say that that solution exists. It is unique, and the domain of that solution, the solution interval, is from 0 to infinity. If I had a different initial condition, like y of negative 2 equals 4, I'm looking at the x value. I'm saying that x value is in this interval. So I would say there does exist a unique solution on the interval from negative infinity to 0. So that's our first order linear theorem. Now we also have a theorem for nonlinear differential equations. So in general, if we have a differential equation dx dt equals some function of t and x here, our goal is to check f and see what t or x values break that, and then also check the partial of f with respect to x, see what that is, and check to see if that is not well defined at some t or x value. So in my example up here, I see that t cannot be equal to 1, and that's really the only restriction in this case. All right, so checking f, I can determine that t is not equal to 1. However, now when I calculate the partial of f, remember this is f, the right-hand side of the differential equation, the partial of f with respect to x, well, I would pull out my 1 minus t, right, that's just a function of t here. I'm really just taking the derivative of x to the 1/3 power. That would be 1/3 x to the 1/3 minus 1, which would be negative 2/3 power, which I could simplify as 1/3 times 1 minus t times x to the 2/3 power. And in this form, I can see that x can also not be equal to 0. What this tells me is that so long as t is not equals 1, my initial condition, there will exist a solution. And then as long as x is not equal to 0, that solution will be unique. So here I have t equals 0 and x equals 4. There will exist a unique solution through that point. However, if I looked at a different initial condition, x of 1 equals 4, for instance, in this case, there would not exist a solution. If I looked at x of 1 equals 0, in this case, there will exist a solution, but I can't guarantee the uniqueness of the solution. And it's also important to note that whatever solution I would generate, if there was a solution to any of these initial conditions, I would really know no information about the domain of that solution. It would not necessarily be defined on the full solution interval. That's the difference between the more general theorem and the theorem for the linear. All right, that really wraps up these two last items that we didn't quite get to in class, the exact equations with the integrating factor and the existence and uniqueness theorems. All right, that concludes this video. Thanks for watching.